Hello everybody, thank you for joining us all again. Today we're going to cover the USB component that's part of the Kyle middleware. This is structured along very similar lines to the networking component. So once you become familiar with the style of how it's coded, it's quite easy to migrate between the different components. It's also portable through the CMSIS drivers onto any devices that provide a USB peripheral. So again, once you're familiar with it, you can use it across many projects very quickly. The USB component is in two parts. It has support for USB device, and also USB host, although the USB host is only available in the Pro version of the toolchain. So we're going to start off by looking at the USB device, and then we'll finish off with host at the end. So the USB device provides the basic core library to communicate with the USB peripheral. And on top of that, it supports a number of USB classes. So we'll have a look through those as well. So there's communication device class, human interface device, mass storage, audio, and if you want to, you can develop your own custom device as well. So in USB device, when we have a microcontroller that has a USB peripheral, it essentially contains the USB physical layer, and we have simply a couple of pins, D+ and D- for the communication channel. In addition to that, we would have typically an external component, a pull-up resistor, that's connected to one of the signaling lines. So either the D+ line or D-, and this basically tells the host what the signaling speed is going to be. In addition, there's high speed. That will initially start as a full speed device and then negotiate with the host to become high speed. Very often now, the pull-up resistor is within a small package, which also provides static protection as well. Simply, it's relatively simple interface that you're just connecting to the communication pins. We have a serial bus, but inside the serial bus, we have a number of pipes, and these are logical connections between the host and the USB device. So the pipes are constructed out of packets which are routed to a particular address and then to an endpoint within the device. And this endpoint serves as a buffer to receive data, and then it will generate an interrupt so that you can read the data. So basically, we have a USB peripheral, usually a block of associated RAM, which we then divide up into these various pipes. And these are either into the host or out to the device. So all of the naming within the USB stack is centric around the PC. So we're going in that way, out that way. Oops, sorry. So we have a number of pipes. So typically, I think the USB standard supports up to 32 endpoints, or specifies up to 32 endpoints. And we have a control pipe at the bottom, and this is always at endpoint 0. And when we connect a device, it always comes up as USB device 0. The host can then negotiate with it, and the device will download a set of descriptors during an initial enumeration phase, and this then tells the host what classes it supports and what endpoints it's got. So typically the hard part of getting USB working initially is to connect to the device and go through the enumeration phase successfully. And then as soon as you've got that set up, it's a matter of streaming data to and from the device. So these pipes, as I say, the user pipes are unidirectional. So we have an in pipe or an out pipe. Within the Kyle software, they are bundled together. So we have pairs of pipes which are set up to make a bidirectional pipe. So when we, in the USB specification, it talks about bidirectional pipes. When we're looking at the Kyle software, these are bundled together to make sorry, I beg your pardon. The specification talks about unidirectional pipes. In the software, they're bundled together to make a bidirectional pipe. So the USB component is structured in a similar fashion to the network component, that we have the physical peripheral, we have the core library, we have configuration files, so we have the RTE device.h that will allow us to multiplex the pins. We have the core library, and that has a configuration file. And then on top of that, we have the device support, the class support. So here we have individual configuration files. So the way of working with the component is very similar to the network component and the file system. Again, like the network component, when we start the USB component, it will create a number of threads. So there's a core device thread which runs the USB stack, and then depending on the device or class support that we're adding, additional threads will be created. So usually it's one additional thread, but in the case of the communication device class, there's a couple of threads. We'll see later that we can create composite devices as well, so we can have more than one class active. So again, if we specify that, then additional threads will be created. The memory for all of these threads is statically allocated, but we just have to keep track of it here. They do support a number of device classes, so we'll have a look through these to see what they're capable of and how we configure them. So we'll start with the communications device class. So this allows us to create a virtual COM port. We can also create human interface device and link up to the file system with mass storage. And there is additionally audio class, which we don't cover today, but that will provide basic speaker and microphone support. So when we are using the CDC device, we will have our application software, which will initialize the USB stack. We can then connect. So this makes the peripheral active and also connects the pull-up pin, so the PC or the host can see that there's a new USB device connected. It will then go through enumeration. So this will be handled within the USB stack. Once we're configured, there are a number of interrupt pipes that are configured in the background and served directly by the USB stack. So in terms of creating a virtual COM port, we can configure the device, and then we have some high-level functions to read and write data to and from the COM port. When we're finished, we can disconnect and then uninitialize. And this will stop the threads and release any memory that they're using. So like we did with the networking class, when we are trying to configure, we'll go into the USB section and take the most abstract part of the configuration. So in this case, we'd start by saying that we're going to create USB with communications device class support. This will make this will show us any dependencies on that class, and we can start to add them. So here we need to say that it's a device class, and the USB stack does support multiple peripherals. So here we can create device, but we can have support for 2 peripherals if we want to. We then include the core library, and then finally we have to choose a USB CMSIS driver. So here in the USB section, we can select either peripheral that we want to work with. So in this case, we're going to use USB 0. So this creates what should now become quite a familiar layout. So again, we have our RTE device.h. So this allows us to do any pin multiplexing, our startup where we can modify and increase the stack. And then we have configuration files for the actual library. So the library itself, and then the class support in here. We also need, simply with the RTX config, to make sure that our user threads are allocated enough memory. One thing to note, when you're doing the pin multiplexing, we're switching over to support the USB peripheral, but there's also the option of having a V-bus sensing pin. Now, this isn't always connected through on the hardware, so if you're not using it, you must make sure to uncheck this, or this will actually stop everything working. So it's one of the common faults that we find, that the stack, you have trouble bringing the stack up initially. Once we've added the configuration files, they're again in this templated format. So here we can configure the library. So again, we can say what signaling speed we're going to use on the peripheral. So this depends on the manufacturer's peripheral, whether it supports full speed or high speed. We also need to provide a vendor ID. So this is a unique number that's managed by the USB Implementers Forum. So if you're going to place a product into the market, you need to have a vendor ID. And then the product ID number is another 16-bit number that's self-managed. This number is the Kyle vendor ID, so I suspect there are quite a large number of devices out there holding that. We can also manage power management on here, so we can say if it's bus powered or self-powered, and then we can also say its power consumption in milliamps up to half an amp. We have a number of language strings that we can also modify here, and we can put in the product name and manufacturer name. All of these settings, as well as configuring the stack, are also used to create the descriptors that I mentioned that are handed over to the host during the enumeration phase. And that takes a great deal of effort out of using this USB stack. In the early days of USB, you had to define all of the descriptors, which are basically arrays of numbers. If you made a mistake in that, then it would just fall over, or if you're using an earlier Windows, it would blue screen and crash. So here we're configuring our USB peripheral, and then these values are automatically used to generate the descriptors. So it does make life an awful lot easier. In CDC, so in the configuration for the device class, again here, one of the major things that we're doing is setting up the endpoints. So these are the communication pipes, and we can select the endpoint number, its packet size, and polling interval. So there are a number of different types of pipe, so interrupt, bulk, control, and isochronous. So depending on the class that we're using, we'll be using different types of pipes. So here, for the control channel that's within the CDC class, we're using an interrupt pipe, and it isn't really an interrupt. You define a polling rate. So this is talking to the host controller every couple of milliseconds, and it's being polled to see if there's any change. We're then using a second communications pipe, which is set on endpoint 2, and this is a bulk pipe. So this is then used to transfer our actual data for the virtual COM port. Down here we can set the communication class definition, so it's interface string, and the size of the transmit and receive buffers. And again here, we've got control of the resource settings, so these are then used to allocate memory into the threads. And generally I would leave these at the default setting, though you can experiment with shrinking them down if memory is a bit limited. So once we have set up our platform, we have a pretty straightforward API for the CDC class. So we can say USB device initialize, and we take the peripheral number. We can then connect, and this will activate the pull-up line. So we'll connect to the host, go through the enumeration phase, and then we can monitor to see if our device is configured. Once it's configured, we can go in and start using the virtual COM port. When we're finished, we can then disconnect. Now, with the virtual COM port, there are a whole library of functions, and many of these are really there to support designing a bridge. So this is where you have a device that's going USB to a real UART. So here, where we've got things like set line coding, get line coding, etc. This is actually reading the settings that are in the terminal program, so we can use them to configure the physical real UART. So if you're just using the virtual COM port to have a way of sending data into your application, then they don't have any real meaning. So you can kind of ignore them. But down here, we've got various functions to send data, write data, put char, read data, get char. So these are more of the ones that are applicable if we're just using the USB as a channel to take data into our application. So here is a minimal program that will start the operating system, configure the USB, wait till we're configured, check to see if there's data available. We can get a character, then echo it back to the terminal program. So this will be a basic bring up test just to see that your COM port's working. In the later versions, I think about Windows 10, then the support for virtual COM port is already built into the operating system. In earlier versions of Windows, we need to provide an INF file, and there is an example of one of these provided with the tools. And in here we can use this but modify the vendor and product ID so it connects to our device. So again, you can sort of use what's already in the tool chain. One of the problem with virtual COM port is while it generally works very well in the lab and the developers using it, as soon as you let this out into the real world, it can become quite a problem. Users have to install the INF file. If it's a non-technical user, they can get confused. The COM port has to be reinstalled if they plug into a different USB channel. So it can cause all sorts of minor technical support issues. So it's very good if you've got a kind of a technician connection, you just want a serial port onto a device, but you need to really think it through if you're going to use this as part of a standard product. Another choice for getting data to and from a chip is to use the HID device, a human interface device. This is the driver that's on every version of Windows, and it's typically used to control mouse and keyboard. However, we can adapt it so that we can send front panel type information. So things like switching on LEDs or seeing what switches are set. And it then provides a very reliable interface between a host and the device. And in fact, I think some of the U-Link adapters that are used with the debugger within the Keil tools actually use the HID interface. So you can build it into a high performance product, and then when user plugs it in, everything just works. You don't have to worry about drivers. They're all maintained by Microsoft, which is nice. So here, again, we come in, we can say USB initialize, USB connect, and then this time we have our endpoints, and these have some callback functions, so get report and set report, that we can modify to send and receive data. So unlike virtual COM port, this is more of a streaming protocol. So these are using the interrupt pipes. So you can set those to to poll the endpoints every so many milliseconds. So it's going to be requesting data to be sent up to the device every 40 milliseconds or so, like what state the mouse buttons are, for example. So it's a slightly different approach to how you would use it compared to a serial COM port. So within our device descriptors, so we send a bunch of these up to the host when we go through the enumeration phase. One of these is the interface descriptor. So in here we'd say we're a HID device, but by modifying the subclass and protocol, we can say actually we're not a mouse or a keyboard, we're a custom device. The host will then start to request report descriptors, and these we use to kind of tell it the shape of the data that we're going to send. So we're sort of, in a way, programming the driver that's on the PC to accept our custom data. Once that's all configured, we can then send and receive data between our device and the HID driver that's within the PC. So again, in a very similar fashion here, we're setting up HID, we're device class, core library, and then we're choosing the appropriate CMSIS driver. And in the version, the demonstrations that are available within the tools, typically the HID driver is then used to control the LED and buttons that are on the evaluation board. So again, here we set up our endpoint settings. So the type of endpoint is an interrupt. So we're using the pair of pipes that are on endpoint number 1. Again, we can set the packet size, and then down here we're describing the report descriptor. So this is the number of input and output reports, and also the size in bytes of data that's going to be sent through those reports. So here we're creating a single report for input and output, and in both cases we're just transferring a single byte to and from the host. And again, we're setting up, we have one thread for the core and then one thread for HID. So this will, we need to remember that the threads that are created will take a K of memory. So now we can say USB initialize or HID initialize, and that will start the stack. Then we have these callback functions to get and set report. And again, these are named in terms of the data flow from the PC. So get report is going up to the PC, set report is sending data down. And then in our thread, our background code, we have another call here, get report, which can asynchronously update the endpoint, change the data in there so that we'll have our new data sent up next time it's requested from the host. So here in set report, we've passed in the type of access that's come from the host, and here we'll have the HID report output. So this will tell us that a packet's arrived from the host, and then we can take that data and use it to set our LEDs. So this is just going to be called every time the pipe is polled by the host. And then similarly, to go into the host, we've got this get report. And this is HID 0, where this is the 0 instance of the library for peripheral 0. And again, we're saying that we've got a report to go up to the host. And in here, we can then populate our data that's about to be transferred. And then in the background, we have this get report trigger. So if we want to, we can talk to the library instance, the report ID, and then give it some data to update that buffer. So we have some fairly simple functions that we need to modify, and this will stream data to and from the host. Now, while that's very attractive as a kind of an end product, it gives us minimal technical support questions because it will plug in, use the Windows driver and go. It's a bit more difficult on the PC end of things. We have to interface to the HID driver within Windows. So inside the Kyle tools, there is an example client. So here in the Kyle-ARM utilities directory, there's a HID client, and this gives us a simple client where we can select our HID device, and then when we push buttons, we can see them on here, or we can set LEDs. The source code for this is available as a within the tools as a Visual C project, and inside that project there's a file hid.cpp, and this has a lot of the low-level functions wrapped up into easy to use functions. So here we can connect to the HID driver. We can list all of the HID devices that are connected. We can find our device. We can then open it, and we've got read and write functions to send and receive data. We can then close it. So a lot of the low-level work is done within this file, so you can easily fish that out and use it in your own project. Though to rebuild this, you need the Windows Driver Development Kit, which I think is now probably just available as a download off the Microsoft website. So there is a complete client in here that helps you build a real system. If you're new to USB, from a software developer's perspective, I think one of the best books that are available is USB Complete by Jan Axelson. This is now, I think, on its fifth printing. I think I read it when it's on its about second, but this does give a very authoritative guide to USB. It provides lots of information from a software developer's view, and it also provides a lot of detail on working with a HID driver. I think she's done a number of other books for things like USB mass storage, although it may have all been rolled into the one book now. She also maintains a very active website. So on there's a HID section, and that has lots of tools and utilities for different programming languages to access HID devices. So if you're planning to work with this, that's a very good place to start. Mass storage probably is one of the more complicated classes to implement, but when we're using the Kyle middleware, it's pretty much a black box to set up. So here we go through and configure our platform. So we can then call USB device initialize and connect, and then it will link up to the file system, and these low-level functions are automatically used between the USB component and the file system. So essentially, we configure it, and then we can just plug a USB. We can plug our board into a PC, and it will appear in the Explorer window, and we can drag and drop files to it. So although, as I say, it's a complicated profile, it's actually quite straightforward to use. So again, here exactly the same, but this time we're just changing to use the mass storage class. And in here we have our mass storage support file. And on, on top of this, we also have to add a template file, which will provide the interface functions between the USB stack and the file system. Again, we have to increase the stack size, and as we're using the file system, don't forget to change the heap size as well. If you neglect that, then nothing will work. So here we have the mass storage support. So again, we need to sort out our endpoints. We can decide on the packet sizes that we want to use, the name of the drive, and then the vendor and product data. We have a number of threads. So again, here we have our core thread, and then we have our mass storage thread here as well. And to make it work, and this is an easy thing to overlook, you need to add this user code template, and this provides the interface functions between the file system and the USB device library. If you don't add this, it simply doesn't work. So these are the low-level functions that do file open, file close from the network library. So you may come and think that you've configured it through the runtime environment, but you're missing the link between the two components. So now, once we've configured this, we need to initialize the file system, initialize the device, the device library, connect the peripheral, and then once we're running, if we plug this in now, we'll see our device appear in the Explorer within Windows, and we can drag and drop files from it. So there is one additional thing that we need to be aware of, and this is again very important when you're working with mass storage class, is that when you're plugged in to a host, the host is in control of the file system. So your code should not try to access the embedded file system while it's being used as a mass storage device. Okay. So there is an additional support file in here, which is the media ownership control. So we can add this file to our project, and this effectively will allow us from our code to connect and disconnect the mass storage device. So this means that if you're plugged into a host and you want the embedded code to update a file, we can disconnect the USB host, update the file, and then reconnect it to the PC. But you must use this file if your code is going to touch the embedded file system while we're connected to a host. Effectively, we're manipulating the pull-up that's connected to either the D+ or D- line. So this pull-up is not connected up to the power rail. It's connected to a GPIO pin, and within the configuration file, we can specify the GPIO pin that's going to be used and the bit state within it, and also whether it's active high or active low. So this is where we want to use a general purpose IO pin. Some microcontrollers will control the pull-up from within the USB peripheral. So there's what's called a soft connect. And then when we tell the peripheral it's connected, it will activate the pull-up pin. So that depending on the device that you're using, you'll use a GPIO pin, or it will automatically be done within the USB peripheral. It is possible to create a composite device, so we can enable a number of classes within the USB component, and then when we plug into the host, they'll both be active. So for example, you can have a HID device and a mass storage class device both within your application, and they'll be active at the same time. Now, when I first came to try this, I thought it'd be a bit of a nightmare to set up, but really it just comes down to enabling the classes that you want. So now we have mass storage and HID, and then in the configuration files, the main thing that we need to do here is really just sort out the endpoints so that our two classes are using different endpoints. And then provided we've got enough resources for the threads that they'll create, it will start up and work. And I did find it actually very easy. It kind of went about first time, I think. So with in addition to the USB device, we also have support for USB host, and this is available within the professional version of the tools. And again, it's structured along the same lines as the host. So we have the core library, we have configuration file for each individual host, We configure the pins through the RTE-device.h, and then on top of the host, we have support for different classes. Again, human interface device, communications device, and mass storage, and we can also create custom as well. One thing you need to be very aware at the beginning is that the USB host doesn't support the hub protocol. So if you have a device, it has to plug directly into the socket of the USB host controller. You can't put a hub and have multiple devices. And I don't think it's on the roadmap to add the hub protocol anytime soon. So again, like device, we have a, when we add the host support, it will create an initial thread for host, and then additional threads for any other classes that we're using. And like device, we can create a host that supports multiple classes. And again, just to have an idea of a bit of the memory footprint and the overhead on the stack as well. So here again, we follow through a very similar setup. So this time we're using host support, and then we can nominate what class that we're going to use, and then CMSIS driver. This time we're choosing the host driver, and we can select which peripheral that we want to use. When we're using USB host, unlike device, the host controller tends to have one of two standard register sets. So this is either the open host controller interface or enhanced host controller interface. There are some devices where the manufacturers decided to do their own thing, so we also have support for custom interfaces as well. And this will be modified depending on the microcontroller that you're using. So up the top here, we decide which part of this is active by choosing the register set that we're going to use. And then we can put the base address of the host peripheral and then fill in the features necessary for our system. So the number of pipes, number of concurrent transfers in the system, size of the memory pool, etc. So again, we have a simple API to start up. So we can say USB host initialize, and then we can look around to see if a device is detected. So with the USB host, we need to, sorry, let me just skip forward a little bit. We need to structure things slightly different so that when we start the device running, we have to have a dedicated thread, which is basically checking for the status of the USB host. So here we're doing USB host mass storage. So this is really looking to see if a device is connected. So when we plug a memory stick in, we'll drop into this part of the for loop. So here we're connected. We can signal to the rest of the system that we're connected, and then we can mount the drive, and then we can perform any additional code that we want. When we're finished, we can unmount it. If we disconnect, we can then set this variable to 0 to say that the drive isn't available anymore. So we have to have a little process within our user code that's basically monitoring the status of the USB host to detect any drives that are connected. What did I miss out? So yeah, we have to, again, like mass storage within the device side, we have to provide this interface file that links our USB mass storage to the file system. So again, similarly, when we're using HID, we can enable HID support in here, device host, and then the core library, and again, select the CMSIS driver. So that will now allow us to start to use HID devices. So we can say number of concurrent devices in the system. So really this is a default of 1. and unless you are going to use a composite device that supports as a couple of different profiles for HID devices, so a mouse and an integrated keyboard, for example. Again, we set up a number of threads, or should be aware of the number of threads that we're going to create. So there's the core thread, and then we have to remember there are going to be additional threads depending on the classes that we're using. And again, we just have to have that memory available. So within the HID, we can do a similar get device status. So again, we need to have another little process running to detect the connection of HID devices. And then we have specific support for getting a mouse state or getting keyboard information. If you're putting a custom device on, we've got this HID parse report descriptor. So as a device connects and enumerates, we can then read its report descriptor to work out how to communicate with it. We've then got additional functions to read and write to the HID device. So here are the high-level functions to manage common HID devices, but we can deal with custom things as well. So as I mentioned, you need this little process, so this is an additional thread within your user code. Here again, we're looking at get device status. So we're looking to see if a HID device has been connected. And in this case, we're now reading it as a mouse. So we get the mouse state, and that will return X, Y, and the state of the buttons that are on the mouse. And again, tomorrow we'll have a look at interfacing that to the GUI so we can create a pointer on an LCD, for example. Like the device, the host can support multiple classes. So again, we can have HID mass storage on the one device. And if we've got multiple peripherals, we can have multiple instances of the library. So we can have one peripheral running as host, another peripheral running as device. There is an additional USB standard called USB OTG on the go, where the host device, or you can connect a USB device, and the two sides communicate or decide who's going to be the host. This isn't supported within the Kyle stack at the moment, though there are a number of microcontrollers out there that do have OTG support. Okay, it's given us a tour through the USB component. Tomorrow, we're going to look at the graphical user interface. This is actually a licensed component from a company called Sega. So this is the Sega MWin software. It's been in development for as long as I can remember, so probably about 20 years. So it's a very comprehensive graphical user interface. It's part of the Kyle toolchain, but there are also, I think, licensed versions by NEC and STM that are available free for use with their tool chains as well. However, the ST have recently bought another graphics company which provides the Touch GFX software. So again, if you're using STM, there is another choice of graphical user interface there as well.